Okay, this week we study vector calculus, chapter 4. This is regarding the curvy linear coordinates. We study the unit vectors for the curvy linear coordinates, and we also study how to compute the differentiation, the derivatives in the space, especially how to compute the gradient, divergence, and curve in the curvilinear coordinate system. Let us first begin with the two-dimensional polar coordinate system, that is r, radius r, and polar angle, planar polar angle theta. That is in the cylindrical, either cylindrical coordinate system or spherical polar coordinate system, that is azimuthal angle. Let us consider a particle of radius a, whose center is at the origin. A point on the circle can be parameterized by a curvilinear coordinates r. Because a is fixed, the radius is, once the radius is fixed, the only variable to determine the position of an object is just angle, theta only. And if we want to describe a point in the two-dimensional space, we begin with the Cartesian coordinates, x1 and x2. The unit vectors of x1 and x2 are constant vectors, and components of this vector a, x, for x1 and x2 coordinates are called the component x1 and x2. The component of E1 can be pulled out by taking the scalar product E1 hat, so that is E1, x1, and the scalar product with the E2 hat, that becomes x2. And position vector x is then expressed as a linear combination of E1 hat and E2 hat. Now the curvilinear coordinates, the circle of radius a and angle theta, and this is x1 axis, y1 axis, x2 axis. These are the coordinates. So x1 is expressed as a cosine theta, and x2 is a sine theta. Because of, if we apply the Pythagoras theorem, the magnitude of x is square root x1 squared plus x2 squared, that is a squared cosine squared theta sine squared theta, that is a. And unit vector, unit radial vector is the radial direction, is just ER is x vector divided by the magnitude of x. That is E1 hat a cosine theta, E2 hat a sine theta divided by a, that is e1 hat cosine theta, so e2 hat sine theta. If I rotate this object on this circle, this position changes along this direction. So if I take the differential, the difference, the displacement from theta to displacement due to the transformation, this guy, in the differential limit, the infinitesimal limit becomes tangent to this circle. And e theta has a component e1 hat sine theta, e2 hat cosine theta. Tangent means that this radius and tangent, they always make a right angle. So er dot e theta should be 0. So because it is cosine, sine, exchange the sine and cosine, and tangent has, in this case, tangent has a positive component for the x2 axis and negative component to the x1 axis. Thus, we have negative side here. So if I multiply these two, this is a minus cosine sine plus sine cosine becomes 0. And we already noticed that er squared, e theta squared, they are all equal to 1. They are orthonormal. Another way to find out the unit vector, we apply this method. So this is what we already have obtained here. We find out the differential. Find out the differential of er hat. Er hat, what we just have found is er hat, this is the unit vector along the radial direction. That is e1 hat cosine theta plus e2 hat sine theta. We call that the unit vectors along the Cartesian axis, x1 and x2, they are always the same. They are always the same at any point. So, if I take the derivative with respect to r, either r or theta, they are all vanishing. So, the total differential of er by varying r and theta together, then we can take the partial derivative with respect to all the variables in here. We have only two variables. This is two-dimensional space. We have two curvilinear coordinates r and theta. So we take the partial derivative with respect to r and multiply the change in that magnitude. And add another contribution coming from the change of theta. So that is er, partial derivative of er with respect to theta, and multiplied by d theta, infinitesimal amount. So if I take the partial derivative with respect to r, as you notice, that this guy vanishes. And again, there is a cosine theta here. Partial derivative, this is function of theta only. Cosine, either cosine theta or sine theta. So if I take the partial derivative with respect to r, er hat vanish. That means er, the magnitude is absolutely 1, but direction does not change at all if I shift r. The radial vector displayed in here does not change the direction if I follow the r direction. It does not change the direction. Next contribution is this one. Er hat, partial derivative of er hat with respect to theta. However, we have theta dependence in both x1 and x2 components. So final result is, if I take the derivative with respect to theta, cosine becomes minus sine, and sine becomes cosine theta. So this is the vector along the direction of changing angle theta. This is partial derivative, so it is in this calculation, the variable r should be kept constant. So if I take the partial derivative of er with respect to theta, what I obtain is the vector along the direction of increasing theta. That means the vector along the direction of increasing theta. It is manifest that the magnitude of this vector is unity. Because of Pythagorean theorem, we have 1. The unit vector along this direction is this vector divided by its own magnitude. However, we have the magnitude 1, therefore this guy, the er partial derivative with respect to theta, is actually the same as e theta hat. That means the unit vector along the direction of theta. In summary, what you find is er hat derivative is e theta hat. What happens to the case if I take the derivative of this guy? The answer is minus er hat. The reason is, here we have er hat e theta hat. If I rotate this in this way, the change in er is along this direction. So along the direction of e theta. Change in e theta is along direction. This is a symmetry. However, the direction is opposite to er. This direction is opposite to er. Okay? Next, we consider the displacement. Actual displacement can be obtained in case we have a radius r fixed to be a, then the only variation can be made along the angle theta. We remember that the infinitesimal displacement to dx from x can be obtained by finding out the total differential. In the case of Cartesian coordinates, this differential is a product of a unit vector EI hat and component xi. We know that EI hat does not change at all, so differential of this guy is just contains this first term dEI hat multiplied by xi, but that one vanishes. And next one is taking the differential for xi and over vector EI hat dxi. This is the differential in the Cartesian coordinate system. Next, we consider the case dx in the two-dimensional polar coordinate system. X in this system is a radius multiplied by unit radial vector ER hat. Total differential of this product of scalar and vector is dr multiplied by unit vector plus r multiplied by differential of ER. This differential of ER can be expanded as components along the r direction and theta direction. So we take the partial derivative with respect to r and multiply dr. Take the partial derivative with respect to theta and multiply d theta. We know that radial vector does not change the magnitude, does not change the direction along the shift in the radial direction. So this first contribution vanishes, and the only surviving piece is this. And again, partial derivative with respect to theta of unit vector along the radial direction is e theta hat. If we substitute this result, this is e theta hat d theta, right? Substitute this result for this guy in here. Then ER hat appears here, and this is dr, and e theta hat and r d theta is written in here. In addition, this is in general, and this case does not have any dr contribution because radius r is fixed in this problem. So this is more general case. Again, total differentials square is like that. So in the Cartesian coordinate system, that is just dx1 squared plus dx2 squared. In the polar coordinate system, we notice that the direction of ER and the direction of theta, that means that is just making right angle. So cosine theta equals 0 for the angle between the ER hat and E theta hat. Therefore, we can make use of, because the angle, they make a right angle, ER and RD theta, and this direction, for example, this direction is the ER hat, and this direction is E theta hat. They are making right angle, so the distance between this will be dr, dr square plus r dr square. Okay. Next one is to compute the time derivatives of unit radial vector. Time derivative of unit radial vector can be found in this way. First, ER is a function of theta. Recall that ER does not have R dependence at all. So if I take the total time derivative, it depends on the angle only. So the way of computing the time derivative is just apply the chain rule for composite function. ER changes depending on theta, and theta changes depending on time. Therefore, we make use of the chain rule. So first, take the partial derivative of ER, unit vector, with respect to angle theta, and then take the derivative of angle theta with respect to time. So this d theta over dt is the theta dot. And what we have obtained according to our previous result, partial derivative of a unit radial vector with respect to the angle is the unit vector along the angle theta. All right. Next, we consider the time derivative of a unit vector along the angle theta. In a similar manner, we make use of the chain rule. We first take the derivative of this unit vector with respect to theta first, and then multiply the time derivative of the angle theta. We remember that in this figure, if I change the angle, ER has a displacement along the direction of E theta, and E theta has the displacement along the direction opposite to the ER hat, right? Because of this partial derivative of E theta hat with respect to theta is a minus ER hat, and this one is theta dot. All right, and then we go further. Second order time derivative of ER. First order time derivative has already been obtained in here. So I take this first order time derivative of ER, right? This one, first order time derivative of ER, and take the time derivative of this one more time. So derivative of product, so time derivative of theta dot one more time, and time derivative of theta or E theta hat once. So if I take the derivative of theta dot, I have a theta double dot with untouched E theta hat. Next one is keep this theta dot the same, but take the time derivative of E theta, right? Time derivative of E theta. But time derivative of E theta is obtained in here already. So substitute this amount in here. You copy this first contribution, angular acceleration along the angle direction, and then minus theta dot is multiplied here, minus the theta dot squared ER hat will be obtained. Next, we take the double time derivative of E theta hat. First order time derivative of E theta hat is obtained in here. So we copy it, minus the theta dot ER hat. And then take another time derivative with respect to time. So take the time derivative of front vector. We have minus theta double dot, keeping the ER hat the same. And then take the derivative of ER hat, keeping the theta dot the same. So we have minus theta dot and ER hat dot. ER hat dot is obtained in here. We copy this result in here. Our final result is angular acceleration in opposite direction minus the theta double dot along the radial direction and minus the theta dot squared along the angular direction. We summarize all results to find out the velocity of a particle in two-dimensional polar coordinate system. Then, this is displacement vector. If I take the derivative, first I take the derivative of radius multiplied by unit vector. And then I keep the radius the same and take the time derivative of ER hat. So ER hat dot is obtained in here. Substituting this ER hat dot in here, what we find is radial velocity multiplied by radial unit vector and R omega, R theta dot. Theta dot is omega, the angular velocity, along the theta direction. Unit vector hat is missing in here. Next, we consider the acceleration of a particle in two-dimensional polar coordinate system. Acceleration is just one more time derivative of velocity. And velocity is written in here. We already obtained the radial velocity contribution and tangential velocity contribution are here. So I take the time derivative one more time of these contributions. First, I take the derivative of radial velocity, then I obtain the radial acceleration, keeping the radial unit vector the same. And then radial velocity is kept, and I took the time derivative of radial unit vector. And then take the time derivative of r, so r dot, theta dot, e hat, e theta hat is copied, and the middle term, middle factor, theta dot is differentiated to find out r alpha. Theta double dot is here, keeping the theta hat here. And then finally, we keep r theta dot the same, and then take the time derivative of E theta hat. Time derivative of E theta hat is a minus ER hat theta dot. And then time derivative of radial vector ER is here, theta dot E theta hat. Theta dot E theta hat. Substituting all these results and collecting the radial contribution and tangential contribution, we find that this r squared theta, and here we have a radial direction. This is r theta dot squared minus r omega squared radial, minus r theta dot squared radial. And what is that? Next one, r dot theta dot. r dot, this is r dot theta dot single one, and r theta double dot is here, r dot theta dot here, but here we have again r dot theta dot along the tangential direction. So there are two pieces, r dot theta dot are two pieces. We have 2 times r dot theta dot here. So there's a radial acceleration, there's a kind of centripetal force toward the center of the origin, and this r theta dot square, so r omega, the r alpha, that is tangential acceleration, and this Coriolis force. Next, we consider the how to transform an integral in the Cartesian coordinate system to another system, such as a polar coordinates. So in general, how to transform an integral in the Cartesian coordinates into any arbitrary curvy linear coordinate system. Suppose that we have a double variable function of x and y in here, and this integral, I would like to rewrite this, reevaluate this integral on the same two-dimensional plane, but by introducing another curvilinear coordinates, for example, r and theta. As you know, the result is integral over r and d theta, and after substituting the value for x and y with the r cosine theta, r sine theta, we have additional factor r in here. This factor is called the Jacobian. Jacobian is just keeping the area in one space, one coordinate system, under a transformation to another coordinate system. But actually the area should be kept the same. In the Cartesian coordinates, the area, calculation of area for this differential, dx and dy, is quite simple. This is a rectangular region whose axes are perpendicular to each other. So the area of that shaded rectangle is just a simple product, dx times dy. We remember that the determinant of three vectors in three-dimensional space, or two vectors in two-dimensional space, is actually the area of the rectangular region, or area spanned by those vectors. For example, we have dx and dy, and there is a space. In 2 dimensions, it should be an area. In 3 dimensions, it should be a volume. Anyway, the unit, this vector can be written in by components of dx and x. And this vector has components of 0 and dy. And determinant is simply dx times dy. We remember that this dx is actually expressed in terms of r and theta, and dy too. and both of them can be expanded as we can make a kind of chain rule. The differential of dx can be expanded as differential of dx with the partial derivative with respect to r times dr, and another partial derivative with respect to theta. In a similar manner, the displacement dy can also be expanded in such a way. We remember this dx is this one, dy is this one. If I multiply the identity matrix and we multiply dx and dy, you will find dx dy. And this dx and dy can be expanded in this way. You know, we have combined these two into in here. In the Cartesian coordinates, this determinant is just 1. In general, this one is in the Curvy linear coordinate system. Dr d theta does make some space generated by change in the coordinates, but actual distance to compute the area should be modified by multiplying some scale factor. This is called the scale factor for angle theta. That can be consistently obtained by computing the determinant of this matrix. That is called the Jacobian. This one is a simple explanation for the two-dimensional case. However, it can also be applied to three-dimensional case too, and even for n dimension. In n-dimensional Euclidean coordinate system can also be re-expressed in terms of n generalized coordinates, this Curvy linear coordinates, as long as they can span all the points in the Euclidean space. All right. Now we define the scale factor. Scale factor, what we have seen, the first example of the scale factor of factor of r that appears in front of d theta for the spherical polar coordinate system. If I consider a displacement of a vector, and if I want to re-express in terms of the curvilinear coordinates, what I have to do is apply the chain rule. Because x depends on q1, q2 to qn, I take the partial derivative with respect to qi, and then multiply the differential dqi. Okay. Then I would get the total differential for the position vector, that is in infinitesimal displacement. We find that this partial derivative keeps all the remaining pieces qj with the j is not equal to I. Qj the same. That means if I change only Qi, then that will generate the direction. The change in the vector is along the direction of that coordinate. Direction of the coordinate means the direction along which the coordinate increases. For example, radial direction. Radial direction ER hat is the direction along which R increases. Theta, E theta, direction along which theta increases. Okay. Therefore, this partial derivative is always parallel to the unit vector along that curvilinear coordinate. To find out the unit vector, we just keep this one and divide this vector by its own magnitude. Therefore, the magnitude of this partial derivative is called HI. That means its name is a scale factor. Only if I multiply this scale factor, the differential becomes some length. This one shows that if I keep everything else, dx is just hi dqi. dqi hat. If I keep all the other coordinates, then displacement along the qi direction is this. You know, hi is magnitude of and magnitude and direction. So if I keep the magnitude and direction, then it is just this vector dqi. Okay, this is the displacement you may obtain along the direction of qi increase. Therefore, this one has the own direction, but this magnitude magnifies the coordinate difference to make its own dimension to be the length. That's quite important. So, scale factor hi can be obtained in this manner. And once you obtain the scale factor, you just divide this scale factor to find out the unit vector along the curvilinear coordinates. For example, you have position vector x and r cosine theta, r sine theta with Cartesian coordinates of x and y axis. You take the radial, you take the partial derivative with respect to r, then only r is erased. This is a vector along the radial unit vector. HR is the magnitude of this vector. So HR is a square root cosine square theta sine square. So HR is 1. You know, radius has the same dimension of length. The scale factor is 1. In the case of theta, if you take the partial derivative, r is kept, and the magnitude of this is r. Scale factor for scale factor h theta for the two-dimensional polar coordinate is r. Therefore, the unit vector along the theta is obtained by this one divided by its own magnitude. That is scale factor. So finally, we end up with the result for the E theta hat in a consistent way. Take a break. the Jacobian. Let us consider the Jacobian of a three-dimensional space from the Cartesian coordinates to a curvilinear coordinate system. It is x1, x2, x3, x1, x2, x3, x1, x2, x3 appears as a row. And this is q1, q2, q3, partial derivative as a column. Okay. If I rewrite this determinant, it becomes epsilon ijk. This is ith component of vector x. Partial derivative of q1, q2, second row, and q3, third row. And this is I, j, k. This is the triple scalar product of these three vectors. This triple scalar product is x partial derivative with respect to q1 cross x partial derivative with respect to q2 and x partial derivative with respect to q3, right? And as we have already obtained, this derivative is just along the direction of q1 axis. This derivative is along the q2 axis, and this is along the q3 axis. And each of them has the magnitude. And that magnitude is just a scale factor along x1, x2, the q1, q2, and q3. If I pull out these three scalar factors, scale factors combines to have h1, h2, h3. And we end up with a triple scalar product of three unit vectors in the three-dimensional space. And for example, in the spherical polar coordinate system and cylindrical coordinate system, these unit vectors are all perpendicular to among one and another. And we usually choose the cyclic coordinates to have this epsilon 1, 2, 3 equals 1. So q1, q2, q3, they are triple scalar product. If they are in order, even permutation, then it becomes 1. So it is, as far as our cases like spherical polar coordinates, cylindrical coordinate systems, all of the case we have this triple scalar product to be 1. Therefore, our final result for the calculating volume in the curvilinear coordinate system is Jacobian times dq1, dq2, dq3. And each coordinate has a scale factors h1, h2, h3. So volume integral should be made by including these scale factors. In the spherical polar coordinate system, x1, x2, this is a cylindrical coordinate system. Cylindrical coordinate system, oh no, it is a spherical polar coordinate system. Z is r cosine theta, and x is rho cosine theta. Rho is r sine theta. This is radius r, and this x, the projection of r onto xy plane is rho, and rho is r sine theta, and this point is r cosine theta, this z component. And then x component is a rho cosine phi, y component is rho sine phi. And then if we substitute rho as r cosine r sine theta, we have x1 equals r sine theta cosine phi, and x2 is r sine theta sine phi, and x3 is z r cosine theta. This rho is the square root of x1 squared plus x2 squared, that is r sine theta. And if I square all the Cartesian components and add them up and take the square root, then you will find r. H1, H2, H3, that means HR, H theta, H5 is 1, R. We will study later, R sine theta. So, if I substitute this result in this formula, integral dx1, dx2, dx3, function of x1, x2, and x3 can be computed to dr, theta, phi, and h1, h2, h3 are square sine theta, and multiplied by function of x, r sine theta cosine phi, r sine theta sine phi, and r cosine theta. So in this way, we can compute the volume integral of an arbitrary function in the spherical polar coordinates in this way. So let us compute these in detail. First, we write down the position vector by making use of the spherical polar coordinates. In the Cartesian components, x1 and x2 and x3 components are written as in this form. Radius r is a vector down. The angular dependence for x1, x2, and x3 are written in the parentheses. First, if we want to find the unit radial vector and scale vector, first of all, we take the partial derivative of the position vector with respect to the radius, the curvy linear coordinate, first curvy linear coordinate. If I take the derivative, the overall vector r disappears, and then remaining piece is kept. You will find that square of all three guys will be 1. Square sine square theta, cosine square theta, sine square cosine square, and then cosine. And azimuthal angle dependence becomes 1 and becomes sine square theta, cosine square theta for the polar angle. And it is evidently 1. So HR, scale factor for the radius, is 1. Next, we consider the unit radial vector. Unit radial vector is this guy divided by HR, and HR is 1. So this one itself is the unit radial vector ER hat. Next, we consider theta dependence. If I take the theta dependence partial derivative with respect to theta, sine becomes a cosine, and cosine becomes minus sine. Square of this vector, we have r squared, cosine squared, open the parenthesis, cosine square phi, sine square phi, and then sine square. R square is a vector down, So we have over vector r, and then this one is 1, and cosine square sine square summation will give r. So the scale factor for the angle theta, h theta, is r. This is displacement partial derivative with respect to theta, and divide this one by its own magnitude, that is a scale factor, I divided by r. Therefore, E theta hat is this one, cosine theta cosine phi, cosine theta sine phi, minus sine theta. Finally, we compute the phi dependence. If I take the partial derivative with respect to phi, then it becomes, where it is, here. Phi dependence has only two terms. Cosine becomes minus sine, and sine becomes cosine phi. And over factor is r sine theta. R sine theta. Alright. The square of this guy, and we take the square root, we find r square sine square theta, sine square phi, cosine square phi. This is 1. Finally, we have r sine theta. The scale factor for phi is r sine theta. In addition, if we divide this vector, this will cancel, and unit vector along the phi direction is obtained in such a way. So, in summary, we have unit vectors along the r, theta, and phi direction. And detailed calculation gives the scalar products of all those pieces. R theta, r phi, theta phi. All of them are perpendicular. Next, cyclic. Is it cyclic coordinates? ER cross E theta. You can follow this calculation by yourself, and this is E phi. E theta, E phi becomes ER. E phi, ER becomes E theta. So we have cyclic form. In addition, displacement along each axis, r-axis, theta-axis, and phi-axis, is just a partial derivative with respect to that coordinate multiplied by the displacement change in the that coordinates. And this one gives everything, gives unit vector along that direction multiplied by its magnitude. Okay, magnitude. Magnitude is just the scale vector multiplied by that coordinate. So displacement has the dimension of length. This one is dr is length. R d theta has the dimension of length, and r sine theta d phi has the dimensions of length. And differential arc length element ds is length squared square root. So along the direction of r, it is dr squared. Along the direction of theta, r squared d theta squared. Along the direction of phi, the arc length is r squared sine squared theta d phi theta. Next, we consider the surface integral. What we have to do is just combine. For example, r theta means a surface made of change of r and the change of theta. This is area. So the cross-sectional area this area, this infinitesimal area element is cross product of ER hat. That means R direction displacement and the theta direction displacement. So we have a product of scale vectors along those directions and cross product of the two. Cross product of the two is just the other one. So R cross phi is R cross the theta becomes E hat phi. The area for area element for the plane on the variation of theta and phi becomes this one, and phi and R becomes this one. And detailed calculations are all given in here. We have volume integral, we have already studied before. The solid angle element is area vector spanned by theta and phi, and that area depends is proportional to radius of sphere. So if I divide this radius sphere, then we have a pure angular dependence only. That is sine theta d theta d phi. If I integrate the whole solid angle element, that sine theta d theta is integrated out from 0 to pi. Polar angle is 0 to pi, and azimuthal angle runs from 0 to 2 pi. As you know, sine theta d theta can be expressed as a d cosine theta, and cosine theta has cosine theta varies from -1 to 1. The final result for the solid angle element, integrated one, is just 4 pi. The area of spherical surface is 4 pi r squared. That it matches our next. Our coordinates, in general, Curvy linear coordinate system has a very complicated structure, but as far as a cylindrical coordinate system or the spherical polar coordinate system is concerned, all the basis vectors along those Curvy linear coordinates are perpendicular among one another, and they have a cyclic coordinate system, and cross products are very simple. Wait a second. Okay. We have about 10 minutes. Let's review what we have studied today. This is a basic, very fundamental relations for our Curvy linear coordinate system information. You need to master how to compute the components in the two-dimensional polar coordinates. And you need to know how to vary the unit vectors in the polar coordinates. So angle dependence of r is tangent, and angle dependence of E theta is minus radial direction. And unit vectors are always obtained by taking the partial derivative with respect to the coordinates, and the magnitude of those vectors are scale factors. In any case, total differential of a displacement vector involves the direction and magnitude. And direction, as far as the Cartesian coordinates is concerned, direction is fixed, so the total differential for the displacement is just a unit vector of Cartesian coordinate multiplied by the change in the Cartesian coordinate, the dxi. However, in the case of angle is related, what you have to do is consider the variation of the unit vector depending on those angles. All those calculations can be made by taking the partial derivative with respect to a given curvilinear coordinates. So step by step, you substitute the position vector in terms of the coordinate and the unit vector along the curvilinear coordinate system, and take the differentials. And each differentials and you need to know how the arc length is calculated. As far as the right-handed coordinate system is concerned, for example, cylindrical and Cartesian and spherical polar coordinates, all three coordinates are orthogonal, and we can apply the Pythagorean theorem. You might want to compute the velocity or acceleration in a curvilinear coordinate system in comparison with the Cartesian case. Cartesian case, for example, dt, dx, is just ei. This is constant, so xi dot, and double time derivative of x, so ei. Still, this is constant, and xi double dot, something like that. However, curvilinear coordinate systems, time derivatives are quite complicated. However, it can be done in a systematic way. What you need to do is how theta r, theta phi, theta r, theta er hat and e theta hat are transformed on the angular transformation, and then by making use of chain rule, you find out the rate, and you'll find a result for the acceleration in the two-dimensional polar coordinates. It involves the radial acceleration and centripetal force, centripetal acceleration, and angular acceleration, and the Coriolis force, Coriolis contribution. Once you introduce the curvilinear coordinates, you might want to compute the integral on the space. In comparison with the case of Cartesian coordinates, you have scale vectors. In the Cartesian coordinates, x, y, z components are all of the components have the dimensions of length, so you don't have to worry about the scale factor. But as far as the angle is introduced, you have some non-identity factor, that is a scale factor appears. The scale factor matches the variation of each coordinate to be the dimensions of length. So in the two-dimensional polar coordinates r theta, hr is 1, h theta equals r. Again, the infinitesimal displacement in a curvilinear coordinate system can be expanded as a partial differential of each coordinate multiplied by the variation of the coordinate. You will find that this partial derivative is proportional to the unit vector along that coordinate system, and the magnitude of this vector is the scale vector hi. And using this expansion, the variation, the displacement infinitesimal variation along the direction of qi is just the unit vector along the qi coordinate multiplied by the length differential. That length differential is the coordinate change multiplied by scale factor. The Jacobian from the Cartesian coordinate to a curvilinear coordinate system was written in a very complicated form, but although it looks very busy, it is simple. If you look at it, is row is a q1, q2, q3, and column is x1, x2, and x3, and all the x's are on the numerator, and all the q's are in the denominator. And this is simply combined as a Levi-Civita tensor because it is determinant, and that is actually the triple scalar product of 3 vectors. And all 3 vectors has a magnitude of the scale factor, and it is parallel to the direction of unit vector along each axis. If you choose the cyclic coordinate system, just like cylindrical or spherical polar coordinates, this one is always 1. And we end up with the scale factor product. For example, in a spherical polar coordinates, hr, h theta, h phi, 1, r sine theta. This product should be included if you transform an integral in the Cartesian coordinate system into an integral in the spherical polar coordinate system. In any curvilinear coordinate system, volume integral involves the product of these 3 scale factors. In the case of n dimensions, you have to compute the determinant of n variables. In such a manner, we were able to find out the expression for each Cartesian coordinates in terms of given curvilinear coordinates, and take the partial derivative with respect to the curvilinear coordinates r, theta, and phi, and find out the magnitude of each. We find out the hr, h theta, and h phi with scale factors. So dividing these scale factors from the derivatives, we end up with the complete expression for the unit vector for er, e theta, and e phi. By making use of these unit vectors, we were able to construct the displacement along each direction and combine them together 2 by 2. We were able to find out the infinitesimal area element spanned by r theta, theta phi, and phi r. Again, volume integral should be expressed in as a product of Jacobian and the differentials of the coordinates. Finally, we were able to check the solid angle element and integrate out all of the angles polar and azimuthal angles, we obtained 4 pi for the solid angle. That's it for today.